Hello everyone, welcome to Gen Z Learning. In today's session, we'll be looking into determining the parallel and perpendicular components of a vector along a line. So before moving into finding the perpendicular and parallel component of vectors in a 3D space along a line, I like to show some concept which we need to know before moving into that. The first one is about dot product. Let's say I have vectors A and B as shown on the figure and the angle between my vector A and B as theta. So the dot product of these vectors A and B will be defined as A dot product of B will be equal to magnitude of A and magnitude of B times the angle times the cos theta of the angle between those two vectors. So theta is always the smallest angle between these two vectors and the theta ranges from 0 to 180 degrees. So the dot product is always a scalar. As you know, if you look at the equation, the product of this dot product of these two vectors is magnitude of A and B, which is scalar, and cos theta scalar. So always the dot product of two vectors will be scalars. So how do we find the projection of a vector along any line? Let's say that I have a vector A and I wanted to find its component parallel to the axis AA and perpendicular to that axis AA. So do that, first I need to find a unit vector UA which is directed along my line AA. So the unit vector UA will say the direction of my projected component of my vector A along the line AA. Once I get my unit vector, then I can get the scalar projection of my vector along this line by getting the dot product of my vector A times the unit vector of my line. So once I get my parallel component to the axis AA, I can get my perpendicular component by using Pythagoras theorem, getting my vector triangle with vector A and its parallel component and its perpendicular components. So I can simply get the magnitude of my perpendicular component by subtracting the square of my magnitude of parallel component from the magnitude of the vector A. So by doing that, I can get my perpendicular component. So I can use my dot product to get my parallel component, and using the parallel component, I can simply get my perpendicular component. So now let's look into some of the examples. So as shown on the figure, they ask us to find the magnitude of the components of this 600 Newton acting along and perpendicular to the segment DE of the pipe assembly. So my force is 600 Newton acted along the line EB, and I need to get the component which is along the line of DE. So my component, if I'm going to get my component, so looking at the direction of my force, so it's pointing from E to B. So if I am getting a component, let's say angle theta, so that's going to be my parallel component of my force, and then I will get my perpendicular component of my force. So how do I find this? So I was given the magnitude of force and the position of F where it's acting along BE, and also I'm given the line DE. So using that, first I need to find my force because only the magnitude of my force is given and I don't know the direction of it. By looking at the positions of E and B acting along, because my force is acting along EB, so I can find the force acting along any line by getting the unit vector and multiplying the magnitude of my force times the unit vector along the line EB. So simply by doing that, I can find what's my force. Once I find my force, then I can get its parallel component by getting the unit vector along the line ED. Why I'm getting unit vector ED instead of EB DE is because looking at the direction of my force, so if I'm having a force like that and if I get its component, then it's going to be pointing from E to D. So once I get that, I'll use my dot product to find its parallel component and also to find its perpendicular component. Okay, so let's look at how to solve this problem. So my first thing, I'm going to get all my unit vectors. So first I'm going to get my unit vectors EB, where my force is acting. So my force is directed from E to B. So for getting that, I need the position vectors. So if you guys don't know what's a position vector, please look into the videos under this channel to learn about position vectors. So my position vector directed from E to B. So for that, I need my position vector EB and divided by its magnitude. So if you are even not clear what's a unit vector, please look into the videos in this channel. So for getting my position vector, I need to get the coordinate of B, position vector of B from the origin minus the position of my E divided by the magnitude of the position vector. So let's look in the figure and see the position of B. So B, I'm looking at B. So from x-axis it's 0, so it's 0I, and in y-axis is 2 meters, so it's 2j, and it is along in the z-axis it's going to be 0. So I have 0I plus 2j plus 0k for my position of B. And looking at the position of E, I can see that for E, my x is going to be 2 meters. And when I come over here, another 2 meters. So that's going to be 4I. And looking at the y, I have 2 meters over here. And in the same line, I have 3 meters. So it's 5j. And looking at z, it's going downward 2 meters. So that's going to be negative 2k. So I subtract the coordinates of E from B, that is 4I plus 5j minus 2k. And then I can get the magnitude of EB. So by simplifying that, I can get my position vector. So that's going to be minus 4I. And then I have 2 minus 5, then that's going to be, negative 3j. And then I have 0 minus 2k, so that's plus 2k. So now I'm going to get the magnitude by getting the square of 4 square plus 3 square plus 2 square. So by simplifying that, I'll get my position vector around 0.7428 i's. And then I get minus 0.557 j's, and I get plus 0.371k. So that now I have my unit vector, I can get my force. So thus my force vector is going to be the magnitude of my force, which is given as 600 times the unit vector EB. So by multiplying this whole term by 600, I get the values of my force. So the components of that is I minus 334.25j plus 222.83k Newton. So that now I have my force vector. Now I can get the projection of that along the line ED. So how do I do that? So for getting my projection, I need to get the unit vector again, acting along my line ED. So I get the unit vector, similar to the previous problem. So we need to get the position vector ED divided by the magnitude of this position vector. So again, it's going to be the position vector of D from origin minus the position vector of E from the origin divided by the magnitude of whatever we got on the So looking at the figure, again the position vector of ED, since E and D is on the same axis and it's only separated by 3 meters in the y-axis, it's simply going to be minus 3 it's simply going to be, let's say this as 0, so it's going to be 0 minus 3, so that's going to be j. So 3j, and then you're going to divide it by 3 squared, so it's going to be minus j. So that's my unit vector of ED. So once I have my ED, I can get my projection. So I'm going to use the vector dot product to get my projection. So my parallel component in ED, let's say parallel, that's going to be my force vector dot product of my unit vector in ED. So by getting that, I'm going to write my force vector, which is negative 445.66 I and negative 334.25 J plus 222.83 K, and then I'm going to put the dot product times J. So if I look at that, there is no x component or k component in my unit vector, so those components will be 0. So it's just going to be the multiplication of my j components, and that's going to be 334 Newton. So my parallel component of the force magnitude is going to be 334 Newton in the direction of ED. So once I have my parallel component, I can get the magnitude of perpendicular component by simply using Pythagoras theorem. So that's my 600, and I got my parallel component along my ED, which was around 334 Newton. So my perpendicular component, it's going to be, let's say E perpendicular is going to be square root of f squared minus FEG parallel component. So the magnitude of f, it's going to be 600, which is given already, and 600 minus 334 square, and I get that perpendicular component is 100 Newton. So my perpendicular component, it's going to be 498 Newton. So those are my values, and that's how we get the components of my force along ED and then EB. Okay, so let's look into another problem. So in this problem, you're going to find the projection magnitude and along the axis of the pole and perpendicular to that axis of the pole, which is OA. So we are given the force. So in this problem, we are given the force, so we don't need to additionally calculate the force like how we did in the previous problem. So here simply we are going to get our unit vector, which is in the OA direction, where the question is asked to find the projection. So we're going to find out the unit vector OA. So we need to get the position vector OA, and then we have to divide it by its magnitude of OA. So finding a position vector from O to A, we need the coordinate of O. It's simply the origin, so no need to worry about that. So how do we get the coordinates of A? So in the figure, the x is given as 2, so we know that it's 2i, and the y it's given as 4, so it's 4i. And the z, we don't know what's that length is. So I'm going to assume that as, let's say, z. So looking at the figure, I can get this length, and I'm given a 60 degrees, so I need to use that data. So you look at it here, so we have 4, 2, so I can find this one by getting the square root of 4 square plus 2 square by using Pythagoras theorem. And by using this triangle, the perpendicular triangle, I can use tan 60, that's why the 60 degrees given, which is going to be my z divided by this 4 square plus 2 square. So my z is simply going to be 4 square plus 2 square times tan 60. So my position vector is simply going to be my coordinates of A. So it's 2i plus 4j plus 4 square plus 2 square into tan 60 divided by the magnitude of this whole term, which is 2 square plus 4 square plus square root of 4 square plus 2 square tan 60 whole thing square. And if you simplify that, you will find your unit vector as 0.2236i plus 0.4472j plus 0.860k. So now I have my unit vector, so I need to get the projection of my force F on my OA pole. So my force times my unit vector OA. So my force is 16I plus 10j, and that's a negative here. So negative 14k. And I'm going to get the dot product of my u, which is 0.2236i. So I simply have to repeat everything here. So now I have to multiply the I coordinates and add it with the multiplication of y and then z coordinate. So 16 times 0.2236 and 10 times 0.4472 and negative 14 times 0.8660. So the magnitude of my projected component of F is going to be 4.07 Newton. So now I have my projected component. So how do I get my perpendicular component? So my perpendicular component, it's going to be the magnitude of my force minus the projected component of my force and then the square root of that. So if you get the magnitude of your force, which is going to be square root of 16 square plus 10 square plus 14 square, and you will get it around 23.49 Newton. So it's going to be your 23.49 minus 4.07, and you will find your perpendicular component to be 23.01 Newton. So those are my projected components for the vector F acting at point A along the line OA. So let's look at the last problem. So in this problem, we are asked to find out the magnitude of the projected component of F along the line AC and to express that component as a Cartesian vector. So the only question here is the projected component, so we don't need to find perpendicular component. And in addition to the previous two problems, here we need to represent that in terms of Cartesian vector. All the other procedures will be similar to what we did previously, but how do we express it as Cartesian vector? If you guys recall, or if you want to check how do we represent a force acting on a line, you can go to the videos on this channel. So if you have a force, let's say, acting on this line AC, so we can express the force acting on that in Cartesian vector form by multiplying the magnitude of the force times the unit vector in UAC. So here for finding the magnitude, so we have to get the projected component of my force acting at C. So that's my first question. So to finding this, first I need to find my unit vector. So the unit vector is going to be AC. That's the question they have asked. So my unit vector AC. So A is my origin, so no need to worry. And in case of C, the coordinates in X is 4 plus 3, so 7I. And it's 4 feet and 2 feet, so it's plus 6J. And it's going downward in 4 feet, so it's negative 4K. And then I can get its magnitude, 7 square plus 6 square plus 4 square. So by simplifying that, I can get my unit vector as 0.6965I plus 0.5970J minus 0.398K. Simply, that's my unit vector AC. So I need this unit vector to find the projected component of F and then to express that projected component in its Cartesian vector form. So to getting the projected component, I need to get the vector dot product. So let's say vector dot product. So for getting the component along AC, I'm going to get the dot product of my vector f and unit vector. So my vector f is 30i minus 45j plus 50k, and my vector UAC is simply whatever the term you have over there. And then multiplying the x coordinates and y and zz, you will find your magnitude as 25.9 for your projected component. So that's my first question. My second question, I need to get it in the Cartesian vector form, meaning that I need to get it in ijk components, right? So for doing that, I'm going to multiply the magnitude, which is 25.9 times my unit vector UAC, which is here. So if I multiply that, I will get my force vector. So if I do so, I'll get it around 18.I minus 15.4J plus 10.3K pounds. So that's my projected component of my force F acting at C along the line AC in the Cartesian vector form. And thank you for watching this video. And if you want more problems solved in statics, please subscribe this video and please leave your likes and also leave your comments